Hi, good morning, Black Hat. I'm Jay Little. I'm a principal security engineer at Trail of Bits, and I've been working in the computer security field for about 10 years. I originally got into it by playing CTFs on teams like White Hatters, 40 Thieves, Hates Irony, Marauders, and I used to run a CTF called Ghost in the Shellcode. And in the past year or so, I've been working on Ethereum smart contracts. It's been pretty exciting because it's like a whole new technology stack. At Trail of Bits, we're a security research and development firm. We're headquarters in New York, but half of our employees are remote. We work in a few different areas. For research, we make foundational tools like binary lifters that are usually based on white papers, and we release as much as possible. On GitHub and open source. For engineering, we make custom security software like OS query extensions, and we also perform security assessments from everything from user space libraries to kernel drivers to blockchain contracts. So for what I'll be going over today, I'll give a quick overview of Ethereum, its virtual machine called EVM, in the front end, the most popular front-end language, Solidity. Then I'll go over a few classes of vulnerabilities that can exist, and I'll show some tools that can help you find them. Then I'll talk about the unfortunate pains of running your own Ethereum software, and then we'll finally talk about how to analyze transaction traces and look at contracts that have been destroyed. So for what prompted this, earlier this year I was working on a project with my friend Ryan Stortz, and we were talking about how to analyze and secure value from Ethereum contracts. One of my parts for this was to get a copy of all the contracts. It's the blockchain, everything should be there. But I noticed that when I tried to get some of them, it just returned an empty value represented by this 0x. And this led me to a whole lot of questions. And that's this presentation. So let's get into some of the details. But first, who here has bought Ethereum before? Oh, wow, that's a lot. And who has sent a transaction to a contract? Oh, still a lot. And who has made your own contract? And has anybody had their contract hacked? No hands. Okay, well, one guy was 50-50, so maybe he doesn't know. So let's get into the basics of Ethereum. Ethereum is a distributed blockchain system. Its killer feature is called smart contracts. These are little programs that execute on every node in the network. This leads to it being called the world computer. It's currently the second most valuable cryptocurrency according to a snapshot on CoinMarketCap. And over the past few years, a lot of banks and have shown interest in it. The mainnet launched just over 3 years ago, so everything's relatively new. A little bit about the implementation. It's formally described in this yellow paper written by Gavin Wood. It's literally yellow. But there's a much more approachable version called the beige paper that has a lot less sigmas and other math symbols. Don't worry, I won't be reading this to you verbatim or anything. I have some better examples. So let's talk about transactions that can happen between accounts. So accounts, think of them like a bank account. They're uniquely identifiable 160-bit numbers. I'm just going to use emojis instead because the numbers don't show up very well on PowerPoint. An address is also like a postal code or a routing number. You can send a transaction to any account you'd like. An account can send money called Ether to another account. And there are special accounts called contracts that have code that runs whenever a transaction is sent to them. These transactions are grouped together into a grouping called a block, and that's what's actually saved on the network. So for a little bit about the Ethereum virtual machine that the contracts run, it's a big Indian stack machine. It's got about 185 opcodes currently. There's more added incrementally over the course of time. The native bit width is 256 bits, and most of the address spaces are also that same width. One interesting part is that about a quarter of the possible opcode address space, that's 1 byte, is used up by very similar instructions. So there's a unique opcode for push 1 byte onto the stack, push 5 bytes onto the stack, and so on. Each of these instructions have a gas cost to prevent infinite loops on the world computer. And things like add and subtracts have a much lower gas cost than storing into the permanent ledger. A good reference for more about EVM is ethervm.io or this EVM opcodes repository I made on GitHub. So for a little bit about what these address spaces look like, there's about 5 of them, maybe 6 depending on how you view a few things. But the important part is that most of them start at address 0. So your code is mapped in at 0. That is where execution starts on every transaction. Storage is for your contract is starts at 0 as well. But most people don't make their contracts in Solidity, in EVM. They write them in Solidity instead because it's a lot easier to use. Solidity is kind of like JavaScript with maybe a little dash of Python thrown in. It's meant to be expressive and pretty easy to read. Solidity compiles down to EVM very directly. It's a very new compiler. It's only a couple years old. The optimizations can literally only get better. And the language has evolved more than it has been designed. They're making incremental changes that break backwards compatibility every few months. So here's an example contract. This code can essentially be deployed directly into the Ethereum network. To go over it, kind of quickly, there's 2 state fields, state variables, owner and jar. Jar is a mapping. Mapping is basically an associative dictionary. The state variables persist across transactions. When the contract is created, the constructor is executed. In this case, it saves the creator into the owner field. And then there are a couple functions, bake and eat. These are callable by anyone on the network. Anyone who has an account in Ethereum can call into these functions. And finally, there's this close function that does a validity check and lets the owner retrieve value from the contract. So in this example, like the owner has been, or the cookie shop has been baking cookies and getting money every time it bakes a cookie because the person has to send in 0.1 ether to bake some cookies. And when they're done, they want to get that money back. And a common way to do this is with the self-destruct function and opcode. So let's look at what happens when a contract's created. Manual creation of contracts happens when an account sends a little bit of money to cover the gas costs for creating the contract and the contract creation code to address 0. So what happens is just what you'd expect. It creates a new contract represented by this robot. The owner is set to who created it, and jar is basically empty. Everything is initialized to 0. So for the corollary operation, close, what happens, like I was saying before, the close function its prototype gets hashed. The first 4 bytes are used as a demuxer, and that transaction gets sent from the owner to the contract. It runs self-destruct, and so the robot sends money back to the owner, and then the contract goes away. After this transaction, there can be no further transactions to this contract. But let's not focus on that depth too much. Let's talk more about cookies. Here's a few examples of what some transactions look like. Anyone can call bake. So here we have 2 calls of an astronaut calling bake and 1 weightlifter calling bake. And at the bottom, there's a representation of what that looks like. So the astronaut has a few cookies, and so does the weightlifter. But let's talk a little bit about eat. Eat takes an argument. This argument is type uint. That is short for uint256. And these arguments are big endian, so this is what the transaction would look like. And as we see, if the weightlifter calls like eat5 to the contract, the contract will just subtract the count, and the state will be agreed on by everyone. Does this look suspect to anybody? There's a little bug in this simple contract, as it turns out. There's an integer overflow on the only subtraction in the whole thing. So what happens if the detective sleuth emoji contract calls eat1 on the contract? Well, storage is initialized to 0, so 0 minus 1 is f, a whole lot of f's. And then here's an example where somebody would have a whole lot of cookies where they wouldn't expect. So that's just one example of something that can go wrong in Solidity integer underflows, but I'd like to describe a few more. For a language designed in this decade, there are a lot of issues that can lead to confusion by developers, can lead to unexpected states, and some of those can lead both to developer confusion and to vulnerabilities. Solidity is working on correcting their tooling and their language specification, but it still has a lot of work to do. I could just go on for hours about all this, but just to highlight a few, type inference and array length are things that are going away in the next version of Solidity because they're just removing that feature. And I'd like to talk about one more of uninitialized variables. This is a contract I found on the Reddit ETH dev subreddit, and this was used as a backdoor. Basically, there's a few state variables in this contract. The important one here is secret seed. And it turns out that when you declare a variable but don't initialize it, it just gets initialized to 0, because of course it would. And so what happens on this line that says seed components S, it actually creates a new a pointer to 0, and when these assignments happen, it overwrites the state variable, so this bottom line overwrites the secret seed. And this was used to backdoor a lottery system. For more examples, we have a repository on GitHub called Not So Smart Contracts. They have concise examples and triggers for many kinds of vulnerabilities. So now giving you a little taste of what can go wrong in a contract, but I'd like to show some tools that can help discover issues and understand them better. I think the best tool out there for analyzing binary contracts is Ethersplay. It's our binary ninja plugin. It has really, really good control flow recovery. A lot of work's been put into it, and it displays it in a nice graph view like this. It also has a dictionary of over 30,000 function signatures, like I've shown before, so it can show you useful information like the name of functions and the parameter types. If you'd rather use IDA Pro than Binary Ninja, I've ported some of the Ethersplay features to an IDA Pro processor module. It's still very much a work in progress. But if you want to look more, if you're used to IDA, you can definitely use that instead. A useful website is ethervm.io. I mentioned this before for its opcode reference, but one day they released a decompiler on their website. So if you don't mind sending your code to their website, it'll give you a decompiler output. It's not perfect, but it's definitely way better than keeping track of a state machine in your head or on a sheet of paper. For another tool, there's Mithril, made by Consensus. It's basically a Swiss Army knife. It can analyze Solidity, it can analyze binaries, it can query the live blockchain for some information, it can perform searches for certain byte sequences on the blockchain or code sequences, and it also has a graph view representation. For some like hot off the press kind of news, Rattle is a tool made by my friend Ryan. It lifts EVM to an IR. That IR has a single static assignment form, and it can do a lot of optimizations and simplifications. It can actually go between basic blocks and summarize code. This is something that the Solidity compiler itself doesn't really even do yet. It can also analyze all the references to a certain memory address or storage address and recover some variable information. This is the example output. It's like a dot file. And for one more tool, it's Manticore, our Python symbolic execution framework. It supports x86 and ARM, but about a year ago, we added EVM support. So it can symbolically execute contract, blockchain states. It's got a bunch of cool features. It can emulate multiple transactions, multiple contracts. It'll automatically explore all the paths in your contract, and it will also emit an output directory full of concrete test cases for it. So that's just a preview of all the many of the tools that are available. There's more every month. So Now for a bit of the ugly part, running your own Ethereum software. This is very much hindsight advice. Before you run your own node, you definitely want to check the storage requirements. This is on the FAQ for Parity and Geth, but the best resource I found is on Stack Exchange. Basically, if you want to run a full node, you will need over 1.1 terabytes. So I'll say personally, I filled up a 500 gig SSD first, and then a terabyte one, and then I bought a 2 terabyte one. Another thing that's not really talked about all that much is disk throughput matters. You're basically maxing out your IOPS for days and days and days. So for example, with syncing Parity, I actually doubled the total disk writes to my SSD just syncing the blockchain. So there's two options for running Ethereum software. They call it a client. I'll just call it a node because our client would be me. So the official implementation is called Geth. I guess the G is because it's written in Go. And it uses LevelDB as its backend for key value store. Parity, the alternative implementation, is written in Rust and uses RocksDB. The public node percentages here are just from a Showdown scan from a few weeks ago. So there's a few different types of clients. Not everybody needs 1 terabyte of space or more to use the Ethereum network. So both Geth and Parity have implemented something called the light client. It can't really verify all the previous transactions, it just trusts they're true. And you can actually use this one on a hard drive according to the docs. I haven't tested that. Most people who are curious about transactions, though, will want to run a fast client. After about 5 or 6 days, it'll be fully synced and you can query it. If you want a full client type that can query any transaction arbitrarily, you'll need at least about 200 gigs of space, and you'll need over 1.5 terabytes if you want to get traces for every transaction. So for options for running these, running a full node is not the default, so I've highlighted some of the options. Basically, use sync mode equals full, GC mode equals archive. That says don't purge your old state. The bottom two options are for performance tuning, and it flushes the disk much less often with the bottom one. And the traces are exposed in the debug RPC API. Kind of equivalent options for Parity, pruning equals archive, tracing equals on. There's many more performance tuning options in Parity. I found a GitHub issue for this TX queue size. Somebody was setting it to max int, but then it would just panic the Rust client, so I wouldn't really recommend anybody turn that on. And they also have some JSON server query optimization, so if you want to be able to query faster. So I have some suggestions. Just when you're running the software, be very patient. If something messes up, just RMRF it. Don't get sentimentally attached to your 600 gigabyte chain data folder. You can re-download it and know that it's right. Definitely recommend using Linux and the fastest SSD you can find. It'll seriously max out. Also, just for anybody who's running their own client, don't also browse the web from the machine running your JSON RPC, because of DNS rebinding, it can be a bad time. So we run software and we just wait a few days and then we can analyze contracts, right? And we can finally start to answer some of these questions. So who created this contract? How do we tell this? Well, the answer is tracing. Here is how to call the tracing API. Parity has a slightly different implementation than Geth. They have different options. But here's what an output trace looks like. And we can actually answer a whole bunch of these questions. We can know what this is the example of a trace for the last transaction sent to the contract. We can see who it's from, this is the actual self-destruct part, because it's saying it's from the contract to a different destination and it has a value. That's how much ether was sent. So if we prettify this a little bit, there's some more information to actually answering the when question. We know the block number. We know who created the contract. And this is a quick summary of all the transactions. The creator of the contract added a little bit of ether to it. So this new account sent some unknown command, and then it sent a command that we know called kill. And then the self-destruct triggered, and it sent the about 0.2 ether to this new account. So was this an attack? Maybe. It definitely motivated me to get through scanning the whole blockchain and seeing what else is out there. But it's a little more tricky than just getting a trace. It turns out that on the blockchain, it's a distributed ledger, not a database. You can't just query, like say, select star from transactions to an address. You have to iterate over every block. And we're doing something that Ethereum isn't really meant to do, because we're going back and looking at transactions from 2 years ago. Most people wouldn't care, but I'm definitely kind of curious. So we have to go through a lot of blocks. So what's in a block? As I said before, blocks have transactions. Transactions have all sorts of metadata, who it's from, who it's to, if there's input, if there's gas, if code was created. And there's also a receipt field that can tell you most of this. And for how we get blocks programmatically, there's a client API. There's two popular ones that are in the Ethereum GitHub. Web3.js and Web3.py. Both have gone through breaking API changes within the last few months. I believe Web3.js has switched over to promises. It can hopefully do some more synchronous calls. In Web3.py, in version 4.0, they switched to Python 3 and totally deprecated their Python 2 library. So I was forced to upgrade everything to Python 3. And for a little bit about how you connect these clients to the Ethereum node, you can use IPC if you're on the same machine. You can use WebSockets if you're curious about streaming events like filters. And you can use RPC for everything else. So here's finally some actual code. This is how you just iterate over every block. We pass a flag to say full transactions equals true. This just prefetches all the transaction data that we're going to need anyway. For each transaction, we get the receipt. If there is a contract address field in the receipt, we know that a new contract was created. Then we can go and check the code. If the code is empty, then it's likely that it might have been self-destructed. There's a few other conditions that I'll talk about later. The other thing we can check for is this status field being equal to 1. This is only available after block 4,370,000 for the post-Byzantine fork, I believe. And this is a much better filter versus an error in creation. But running this client software isn't always so easy. A lot of times you might not get synced fully. For example, if you see Geth saying imported new state entries or updating chain data, don't try to query it. You won't get valid results back. And sometimes you won't actually get caught up to the current block. Sometimes parity is not any better. If you are running parity and you're looking in your console and you see this yellow number to the left, that means you can't query past that block number and get any valid results back. Also, I found out in the current version, if you turn on a lot of archiving options, it'll crash eventually. But don't worry, I reported that, and they're working on a fix. So with these clients not able to always get us what we need a solution, and there's only one hope, and it's etherscan.io. It's really a great resource and website. They've done the database query for you, basically. So for any contract you want, you can get a list of transactions in a few seconds just by using their website. They also have some features where contract authors can upload their source code and verify that it's what they say it is. So we'll take a hybrid approach. we'll run our local software to do that code that I showed earlier, just to get a list of all the contracts. And then for getting the traces, I'll use Etherscan. They have an API, actually, that'll list both internal and external transactions. Their website does say to limit to 5 queries per second. So if you have tens of thousands of contracts you're curious about, like I do, it'll take a few hours, but it'll finish eventually. So finally, some results that we can talk about. So I queried from block 0 to 6 million. That was from a few weeks ago. And found out that there have been about a total of 2 million contracts created in the Ethereum network on mainnet. And of those, about 55,000 are empty, the 0x. So I was like, oh, wow, I had no idea what to expect. I just looked at my, I just did an ls and wc-l, saw how many there were. But I got curious, like, what if I MD5 them? How many of these are actually unique? And it turns out about half of them are duplicates in some way. And the other thing to note is that about 32,000 of them were empty and had a balance of 0. So there were some that are empty that had a balance, and that was kind of weird. Because if they were destroyed by a self-destruct, they wouldn't have any balance, because it transfers all the balance to the argument. So I started looking at what are these 0x contracts, and it turns out the first one is kind of an interesting case. We're almost at the 3-year anniversary of this. This was the first attempt at creating a contract. And I say attempt because they didn't pass in enough gas to create it. I believe when it hit this S-store uses 20,000 gas, and they just didn't send enough. But if you use the clients to query this, it just returns empty. Later that day, there was a contract that was quote created that was empty, but it doesn't have any code in it. They just sent an empty transaction input value. The kind of disappointing part of this is you'll see in value, the person who did this sent 14 Ether to this. So now this contract that has no code permanently, forever, has about $7,000 of Ethereum in it. But later that day, there was a contract that was created successfully. But just to kind of show that there's noise in transactions and that everything is immutable, a couple months ago, somebody decided to send 420 in Wei as value to this contract that doesn't do anything with it. And then later that day, somebody also sent it 69 Wei. So I was curious about more of these duplicates. So I just did like unique-c and saw what was the most common one. And this was kind of interesting. The contract here, basically, it just infinite loops. It kind of jumps back into itself in a few spots, and it calls code copy, which takes the code you see here and copies it into memory. It turns out that some people on Stack Exchange say that this is a network DOS, because it just would keep reading code, and several accounts sent this about 10,000 times. To go along with that second example from before, there have been about another 10,000 accounts created that have a total of about $2.5 million, but they have no code behind them, so there's no way to get it back. For one more example of duplicates, this one was kind of funny. It was just really big. There were 6,000 nulls in this contract code, so it doesn't actually the contract doesn't actually do anything. Because null is the stop-op code. But that 6,000 number is kind of interesting. I noticed that in this EIP, basically the RFCs for Ethereum in 170, the maximum size is hex 6,000, so maybe whoever was trying to fill up the blockchain had a hex versus decimal conversion problem. Then there's one more interesting example, and here we actually have a real self-destruct. There's a few thousand of these, where they just push an address and call self-destruct. That's the total purpose of this contract. And in the transaction trace, they all send 0, 1, or 2 Wei, basically nothing. Like even like an add opcode costs 3 Wei. So I went on Etherscan and looked at what this looked like, and we just see this huge list of self-destructs. There are, I think, about 500 in this transaction. And it was actually, I was like, wow, what's going on? This is really weird. I hadn't seen anybody really talk about it. And it turns out that this is the net effect of that transaction. What actually happened was there were a whole bunch of contracts created. Each one was set to send a message to another one that would then self-destruct and just kind of spam out on the network. This only happened a few times, but it definitely filtered out a whole lot of transactions just because it was just a whole lot of noise. There were about 3,000 or 4,000 of these in total. So after all that filtering, I'm down to about 2,000 contracts. I think it was, on the previous slide, it was like 1988, round up. So we filtered out a lot of spam, some DOS attempts, a lot of noise. And let's get into some specific criteria for finding these cases of self-destructs. So I'll just kind of give a high-level overview with some more emojis to explain what we're looking for. So if somebody creates a contract, that's totally normal. So some things we might be interested in is when the owner sends a self-destruct to the robot contract, and then that ends up sending money to a different address that wasn't the original creator, that can be a red flag. Another red flag would be is if somebody who wasn't the original creator causes the self-destruct transaction. So let's do some more filtering and see what meets these conditions. So again, from the trace, we know the destination of the self-destruct transfer. And when we filter who was not the original creator, there's only 630 contracts. And a kind of depressing fact about 10 of those is they self-destructed and sent their money to address 0. So it kind of burned it forever. The most unfortunate of these is somebody sent 50 Ether, that's several $1,000s in this transaction. And in the Etherscan trace, the owner called a kill command that took an argument called 2, and it just was all zeros. So I don't know if they did this intentionally, but it is kind of unfortunate to see somebody lose what's like $20,000 in today's value. Another one of these transactions that I got kind of excited about was the largest self-destruct in history, where it sent 10,000 ETH. But I think this is, after looking at the transaction traces, I think it's okay. I can't be completely sure because I don't know who all the accounts are. But in this contract, it implemented a parity multisig wallet that was likely vulnerable to this init wallet attack. Basically, there weren't some initialized variables in the constructor, so it was done by a function later, but anybody can call that function and potentially influence the state of it. So the first transaction to this contract was calling a init wallet. But I followed it later, and nobody transferred in 10,000 Ethereum to it. The 10,000 Ethereum transfer happened as the self-destruct happened in the same transaction. So I think this was actually a system set up as part of a token pre-sale, and they just happened to get lucky and nobody redirected their transfer. For one example of this parity init wallet attack, at the bottom of this slide, these are the actual attacks that are probably the largest ever on the Ethereum network. This one person got over 120,000 Ether in a couple minutes doing the attack, but it wasn't this one, so I was kind of bummed about that. So let's do some more filtering. And we have these then we'll have from 630 down to about 160 transactions where the originator of the self-destruct wasn't the original creator. And then just looking at these, there's only 25 that have sent more than 0.1 ETH and 16 that sent 1 ETH. So there actually hasn't been a lot of these like mass hacks using self-destructs. But because there's so few, I kind of like look through everyone, and I'll show you some of the results. So this was one of the largest transfers on a self-destruct, where 300 ETH was sent to a different address from from a transaction that was not the original creator. But going through the trace, we find out that this was actually intentional. This first argument from was the original creator, and they just the contract was coded to allow somebody else to be the owner. So this was actually a totally okay thing to do, and they were just using the Ethereum features. This will be a little bit of a trend, as we'll see. So this one kind of stood out to me in my list because it has a really interesting address. It's like DICE. And it turns out that if you look at the creator, they've created several contracts, including some that have source code available. And it's just a gambling game. And this is yet another example of where the transaction came from somebody else, but it was actually totally intentional. And this one sent 65 Ether. That's a lot. So turns out there's even more gambling on the blockchain. Here's another one that turns out to be intentional. It's called EtherWow. The Google Translate says it's the most popular blockchain guessing digital game in China. I'm not so sure because there's only been a few Ether ever transferred into any of these things. And in a different version of this, the creators created several contracts, and if you trace through them, one of them has source code available, and there's this really dramatic comment above their owner kill function to be very careful, emergency only, for contract upgrading. So again, this is yet another example of these large transfers, but it doesn't look like it's an attack. It's just the design of the contract. So I finally have one that's a real example of a likely attack. Basically, there's this contract that ended up calling this mortal function, and it was the exact conditions we want. It was somebody who was not the original creator of the contract. The destination wasn't the original creator either. And I can't be sure exactly what happened because we don't know the intent behind everything, but what it looks like is somebody copied some code from this mortal contract, which its intended functionality is to initialize the owner. And if you're the owner, you can kill the contract. But I think somebody probably renamed the contract, therefore exposing this mortal function to anybody, because somebody totally called this function and became the owner and got a couple Ether. So what have we learned from all of this? There's not a lot of epic attacks on the blockchain. A few of them do happen, but it's really difficult to go in and tell what happened a few years ago to actually analyze this. I couldn't even do it on my own computer. I needed to use Etherscan to help fill in a lot of the blanks. So if you're an Ethereum developer here, I'd strongly recommend you understand and fix all of your warnings. Maybe use our Echidna testing framework to help make better tests. Just be really rigorous. If you'd like some help performing an assessment on your contracts, definitely get in touch with us. We're very thorough. If you're a security researcher, become a blockchain explorer. It's kind of fun. You fill up your whole hard drive and you can do some SQL queries later. But remember to have patience, and if you're into symbolic execution, check out Manticore. And thank you for your attention.